Okay, this morning I want to talk about a concept. At the outset of this talk, I want to make sure that you understand that this is a concept and it's under development. And it really has to do with can we find and what can we find in terms of connection between innovation and green chemistry / green engineering. As we look into this matter, we develop a philosophy. Just stating before you, as many of you have already stated, we are using the concept of sustainability. In this case, I think this states it very clearly. We want to leave something behind after we leave this planet that's useful to future generations. And green chemistry offers a transformative framework to permit us or help us in that gain or that aim of sustainability. I took this right out of the annual review of environmental resource, and I think it states it very clearly. This green chemistry and engineering, by that we want to maximize the efficiency and minimize the health and environmental hazards through the chemical production process. And I think that's an interesting approach. It may be limiting because there may be other areas that fit into it, but at least it's one statement. So what do we mean by innovation? And I think that this word balloon or cloud that we have here that I actually stole from the EPA innovation site tells us, at least in part, what people think of innovation. It's all over the map. You know, as I've pointed out in the first point, it's in the eye of the beholder. And maybe we can use the paraphrase of the former Supreme Court Justice, I'll know it when I see it. But innovation clearly needs to be formulated in a context. So perspective and context dominate the selection of features by which we judge innovation. And then when we think about innovation associated with green chemistry and engineering, so far there are statements as to the innovation, but the number of tools out there that actually show us in terms of evaluation, they're very limited. So if we think about innovation, what is it that we really mean? Innovation that I'm using today starts with idea formation, evaluation of that idea, selection of different opportunities within the context of the idea, development of a technology arising from that selection, and then providing new processes or new products that contribute to a reduced environmental footprint in this case. So green chemistry in our objective is seen as a leading force directing chemical synthesis and production for the innovative design of processes leading to more sustainable environment. Can we, in this objective, can we actually see accomplishments of green chemistry and evaluate them in the light of the guiding principles to actually point out where innovation has been accomplished? So why are we looking at this? Well, there's a need for a metric. A metric is nothing more than a way to gauge changes along an established line of thought. So first of all, we need to understand sources of green chemistry innovation. There are awards being given out. There's certainly that's a great source of looking at innovation. And when we think about the utility of metrics, if we are able to link them directly to innovation, we may be able to use them as guiding tools for new opportunities. And then also, as we look at this process, we are evaluating the relative importance of green chemistry, green engineering principles. I think a lot of us have said we really believe in them. This is an opportunity to show that it really is there and has great value. One of the ways in which innovation has been evaluated is offered here in this slide that is condensed from the World Watch report of 2008 on innovations in the environment. And these are the ideas that they actually looked at: innovation cost reduction, emission cost reduction, innovation cost and benefits, and then they had policy influence such as technology progress, environmental management, innovation induction, and also self-regulation. Another effort going back a little bit further, and this was championed to a large extent by Dow Europe, it was the eco-compass associated with eco-innovation. And so these people in Europe looked specifically at the idea of innovation and said to themselves, if we want to support the ecology or the proposed ecology that we would like to maintain, what are important? So resource conservation became one. I think that's manifest and is certainly included in green chemistry. Environmental and health protection, risk reduction was part of that. Mass intensity, energy intensity, use and revalorization were elements of this, and also use intensity of the product or process. And what did they get out of this? Essentially, the red line suggests a performance, and this is just a test case showing you that different innovations have different characteristics in this matrix and displayed on this radar graph as where they actually stand and perform the greatest. The score at 4 would obviously be the best in all circumstances, but many innovations don't get that far. Other ideas that we've had internationally, the BASF ecological footprint offers much of the same kind of scenario. The mapping, it looks attractive. It certainly has interesting colors. But the real problem that I personally have with this approach is that I don't understand it, and I don't really understand how to gain access to the understanding behind it. If they tell me that land use is important or less land use is there, I really have to accept that metric or the metric they have without really any understanding of the basic process that's involved. So in all indices, that is a problem. The real question becomes one of how did they actually make the decision in getting to this fingerprint? Can we explore the data that went into it? And to a degree, the eco-efficiency portfolio, again, BASF has championed this very strongly, suggests similar type scenario. Here's the green principles espoused in essentially very few words. So the green chemistry, 12 green chemistry principles to the left, and the 12 green chemistries of green engineering to the right. And the one thing that I was interested in looking at as I compare the two is that there is some overlap between the two. And so the question becomes one, can we distill this down to a discrete number of elements that would be useful as judgment criteria? And one of the ways in which I've started out on this, remember this is still concept approach, is to use what was offered in green chemistry some time ago, these two formulations of engineering and green chemistry using letter designations. And what I did with that then was to say, okay, let's see how we can unify that under different concepts. And here's sort of a working sheet that I have used in the past. And I came up with using green chemistry, green engineering, again, using the very same letter labels that were on the previous slide to sort of give you where that was important within the context of either the engineering principles or the chemistry principles. And out of that consideration, I offer to you that we have a possibility of using these 7 criteria. And it becomes mass utilization, reaction control, renewable materials, waste prevention, safety, and toxicity. And so that's one of the things that's confusing here is material diversity is not included in that. I will show you how that works out in the future. So these are the components that I assembled as my 7. And then the question becomes, how do you actually characterize these components? And these are the different elements that I've put under each one of them. If you look at mass utilization, reduced mass intensity, recycle options, efficiency, availability, and design for degradation. Not all of them are chemistry, not all of them are engineering, but hopefully they are a blend of the two. And so on as we go through the different components. The other thing that you will note is in this first slide, mass utilization, the 4th item is availability. Availability, at least for this schema, is involved in both component criteria, meaning different things. Maybe I need to express it with using a different word. And here's the others. If you look at toxicity, just to give you an example, ecotoxicity, human health, reduced emissions, reduced product toxicity, and no bioaccumulation. All of those are features of an invention that could be utilized as a marking or a measurement tool. And my intent then is to use the radar diagram that we had in the past and sort of map out where a given discovery, invention falls in this map. My example that I'm going to use today, just to sort of show you how this system might work, is from the area of renewable feedstocks. Renewable feedstocks are important to us in terms of sustainable chemicals. We have with them reduced emissions, reduced energy, smaller footprint, and renewable feedstock. As we extend that more specifically into the item of interest that I'm going to offer this analysis for, it has to do with industrial chemicals arising from bioprocessing techniques. And so again, we have a renewable feedstock. Energy consumption is reduced. We have the opportunity to sequester CO2. Source pollutant reduction is there. Downstream separation improvements offer some significant utility and waste reduction. Downstream conversion also offers some opportunities to make other products that are attractive environmentally. The item I'm looking at is the invention and process that Geomatica put together for 1,4-butane diol. The process objective in this case, and What I'm using essentially is 3 published articles that Genomatica put out. So that's the limit of my universe when I really talk about this one product or one discovery. So sucrose to butanediol. So they would like to have an organism that actually is capable of fermenting sucrose into BDO, or butanediol. And the way they did this, I found this to be really remarkable because they espoused a chemical biology approach to reagent and synthesis strategy that we would have in chemistry, but they've used it essentially in a biology context. They used reaction operator management. We'll talk a little bit further about. Network calculation, integration with simulation software. They did pathway tracing and pathway ranking and analysis. Now, we'll get into that, why those are important. In the reaction operator management, they used a known chemistry and enzyme class to actually, as a directive force. They enhanced a biopathway predictor database with these operators. So they were using chemically based operators and directions to elicit biopathways. And they also were very concerned about secondary metabolites, because secondary metabolites, if they're unwanted, are essentially waste if they can't be recycled. When we look at the reaction network calculation, this approach used a target compound in a simulator database. We heard a little bit about that in an earlier presentation relative to drug design. They went to constrain the network size and then calculate the network. They used automated integration with the simulation software of this information. So secondary metabolites were involved directly in the network reactions. They went after balanced reactions and equations. Thermodynamics were used in terms of the properties to trace where and how the energy flowed. And they also were concerned about identifying known biochemical reactions. They did not necessarily want to invent a new one, but they wanted to go with ones that they knew. Pathway tracing was used starting metabolites from the calculated network. They selected maximum pathway length to avoid intermediates that might clog the system and become side products. Trace pathways were used using starting materials, more than one starting material to get to the 1,4-butanediol. And then finally, thermodynamic evaluation of the net pathways was important because this had to be placed in the context of a single microorganism. So the pathway selection and analysis evaluated all the pathways for the maximum theoretical yield for the metabolic model. Then they ranked the pathways and using different selection criteria that they exposed. To me, this was rather remarkable that they were able to give this kind of detail, because this is design detail that many times a for-profit concern will hide. And they evaluated the results in terms of yield and novel steps. This is the pathway that was introduced into E. coli. They could use either succinate or alpha-ketoglutarate as starting components and going through, as you can see, succinyl coenzyme A through to 1,4-butanediol. So the pathway to development features, now going a little bit further, they were able to show that they established a new biochemical pathway. They have knowledge of the pathway the metabolite pathways and metabolism. Why? No side products. They want to avoid side products. They developed a biopathway prediction algorithm. This is all technology that in previous considerations was completely missing. Nobody had this technology at all. So this is a remarkable computational side invention, just this in and of itself. The model producing the metabolic engineering strategies for balancing the engineering energy and redox requirement was unique and highly innovative. They used and developed two heterologous pathways for 1,4-butane-diol production in E. coli. So they're using two different starting materials, or they have the possibilities of using two different starting materials. And let's underscore again, we have renewable feedstock utilization. And this is the way in which that first stage has been evaluated according to my rules. As you can see, material diversity enters into it. Mass utilization is very important. Ecotoxicity is different because all I'm considering right now is the effort from the bench up to mid-scale operation, not full scale. And this is the way in which the radar graph actually comes out, showing you where they showed the best. Now let me just move on. This is the BDO process, sucrose to butanediol. Downstream cleanup is very important to making this process work. And so in this next section, I want to just look at the ideas of process development features. They have credits for steam and energy. They have designed fewer unit operations, a smaller plant footprint, and the processes are engineered for safety. They also conducted an LCA analysis. I have to speed through this because I have little time. In this now larger context of the entire process, we're looking not just at the invention, but we're looking at the invention through to actually implementation in the field. And this has been brought up as a technology by BASF. This is the way in which that innovation can be depicted in the radar diagram. So in a rush measuring invention, why do we want to go there? We want new ways to use traditional indicators. We want to understand experimental indicators to help us provide insight into new areas of devoted research. I do believe that this can be worked in that direction. Gap and challenge measurement is part of this agenda as well. And then the overall research agenda is expected to expand. Expected results, increase new ideas, because we are now actually mapping where innovation occurs. People will be attracted to past innovation and want to emulate it, and they'll also find opportunities in areas that are poorly or a little utilized. The idea quality improvement will be there. Efficient optimization of quality ideas should be part of this effort too. And we also can explore the green chemistry, green engineering principles for new developmental opportunities. With that, thank you very much for your attention.
Okay, do we have any questions for the speaker?
At the start you mentioned how with the principles of green chemistry and green engineering, there was a lot of overlap, and you were looking to try to bring those together. And with your tables, you were able to illustrate that very well. My question is really based upon the link between biodegradation and ecotoxicity, where further overlap is toxic to the community. So certainly in our experience, we found that normally that piece of information is buried in the electronic supporting information and not commented upon because it's just a validation criteria.
Sure. Well, hopefully I pointed out that there were businesses of where degradation was going to be covered as part of the analysis. Yeah. And so in that context, I certainly agree with you that degradation has got to be a component. One of the questions I throw back at you, quite frankly, as a presenter, is if you look at what I've done so far, where do you see that I can improve it? Because I'm really anxious about improving it, making it better in terms of an overall analytical tool. I'm not suggesting for a moment it's there, but I'm just saying this is a start. This is one of the things I'm trying to do. What I'd like to do is to find new and better ways to assemble this information, if there are.
I think it's just a response to that would be that essentially when you're whittling down from 12 down to normally there was only about 5 key terms in your tables. I thought it was very interesting that the design to degradation was still in there. Yet when I think many people in the green chemistry community see the 12, they see the design for degradation as, well, it's in there because it's a good idea, but do I need to really worry about it? I'll go off and do my own thing.
Right.
So I thought the fact that you've analysed the 12 and kept it in there made me very happy, to be honest.
Okay.
But my comment also is that when you had your table called toxicity, and then ecotoxicity was the first term, I would just state that that would also encompass the design for biodegradation within like a subset of that term, so it hasn't been lost at that level.
All right. Yes.
Thank you. My question is to the last the example you have, the
1,4-butadiol
case.
Yeah.
And after a year reading your assessment of yours, and still I couldn't compare to the present industry's material.
I'm sorry, you couldn't compare it to what?
The butadiol now is making for 3-way. I guess one from the 2 pounds butane, and one from the
acetylene, yeah.
And the other from the alcohols, PO oxide.
You're quite right.
Then your sugar chemistry, you lay out all the green chemistry part, how important, and seem to be all qualitative, and how it can compare to the present the process. That is a part I think I have no connection or something to really evaluate how this can substitute eventually.
I certainly can understand your question, but I had a quandary. I could talk about chemical production of them, and there's no doubt about that. There's a lot of information about those. Each of those have their own problems, notably in terms of waste prevention issues, and also byproducts, and also footprints. So the larger footprint is significant. But my purpose today, at least for this talk, was to show you a concept relative to a discovery which I believe was quite unique. And it showed the development of new technologies that related to areas of chemical biology, green chemistry, and green engineering. And so I used it as a test case just to show you how far this kind of analysis could go. I'm not suggesting for a moment this is the end point, but to me it's a starting point. What I would like to do beyond this is to ensure that the different components that I've identified, those 7 components, that they contain all of the features that are necessary. Right now, they're there, and I just need feedback and conversation and discussion with people who know a lot more than I do.
Thank you.
Thank you.
Thanks. I entirely agree wondered a little bit about the point that you think that concept of metrics, of measurements, of somehow regulations would induce new ideas. I think that is contradictory a little bit for me, because regulations normally do not produce new ideas. Can you probably comment on that?
Sure. First of all, this is not meant to be regulatory. So that's one of the things I wanted to clear up. I don't work for the regulatory side of EPA, by the way. But in that context, what I think is important is you have lots of discussion in the society about it, or you have a lot of discussion about innovation in the society. Business typically uses it to guide where they want to put their money. They've done this quite well through time. But in this case, what I'm really aiming at is to say, okay, we're looking at the technology and discovery of chemistry and engineering. And we're asking ourselves, where have we found the innovation? And that's all the question really is. This business of, it can have guidance, definitely has guidance, because if we find success in one sector, in one area, people may say, okay, I really want to go and do that too. In fact, the people who discovered this system or went after this system, they cited the work of DuPont in their 1,3-propane diol work. So I don't want to do this in the context of regulation. I'm looking at this strictly in science and technology and saying to you, how can we actually look at green chemistry and look to use the mapped information and use it to our benefit to point to opportunities?